In this video, I'm going to prove Descartes' rule of signs. Basically, it says if p of x is a polynomial of degree n, if p of x has s sign changes, then p of s has either s positive roots or s minus 2 positive roots or s minus 4 positive roots. If s is even, eventually you'll get down to 0 possible positive roots, and if s is odd, you'll get down to 1 possible odd root. It will have at most s roots or 2 lower or 4 lower or 6 lower. Okay, let's get into this. We're going to consider only polynomials whose leading coefficient is 1. So if you have 1x to the n plus a sub n minus 1, x to the n minus 1, a sub n minus 2, x to the n minus 2, all the way down to plus a 2x squared plus a1x plus a sub 0. Now note that since the coefficient of the leading term is bigger than 0, positive, that the limit as n goes to infinity of p of x is infinity. What that tells me is that I may not know what's going on in here, but sure enough, when x gets really large, it's going up to infinity. That we do know. And that's going to be important. So some notation. Let s equal the number of sign changes in p of x, and p is equal to the number of positive roots. Now, just so you know what I'm talking about when I say sign changes, or the number of sign changes, let's make that to the fourth. Minus 2x to the fifth, minus 2x cubed, minus 4x squared, plus 5x minus 6. The first term is understood to be positive. From a positive to a negative, you had a sign change. From negative to negative, no sign change. From negative to positive, you had another sign change. From positive to negative, you had another sign change. This polynomial has 3 sign changes. So that's what we mean by a sign change. Okay. So now, what I want to prove is the following. This is my goal. I want to prove that s minus p, is a non-negative even number. That is, the number of sign changes minus the number of positive roots. It's an even number, and it's not negative. It's non-negative. Now, we're going to do this in 2 parts. First, I'm going to prove that s minus p is even. And then in part 2, I'll show that it's greater than or equal to 0. Putting those 2 parts together, I will have established that s minus p is a non-negative even number. So part 1, like I said, I want to prove that S minus P is an even number. Remember, -2 and -4 and -6, they're even numbers. Now, we're going to do this proof in two cases. Case 1. Suppose the constant a sub 0 is greater than 0, and case number 2 will be when a sub 0 is negative. Now note that P of 0 is a sub 0, because 1 times 0 to the n is 0. This constant times 0 to a power is 0. This constant times 0 to a power is 0. Same here, plus a sub 0. Okay. Now, if a sub 0 is positive, now again, we're only looking at positive roots right now. So I don't care what happens to the left of the y-axis. If a sub 0 is positive, so it's up there. P of 0 is a sub 0. Okay? P of 0 is a sub 0. Now, the graph can go like that. That would be that P is 0. There were no positive roots. Or maybe P comes down and just touches. We're going to call that a double root. We're going to say P is 2. Or maybe it crosses like that. Remember, where are we? Remember, it has to come back up and go to infinity. Here, we had two roots, 1 and 2. So P is 2. Is P always 2? No. It crossed once, it crossed twice. Now, to come back and cross again, it's going to add 2 more roots. 1, 2, 3, and 4. Here, P is 4. What if it goes like this? And they all should go through a sub 0. Suppose we have this one. It has 2 roots so far, and then it comes down and it just touches, but we count that as 2, and then it goes up. So P would be 4. And again, if it came down and back up, it's going to be 2 more. And if it came down again and went up, it's going to be 2 more. As long as it crosses or touches the x-axis. I mean, of course, if it just came down and went up, that doesn't add any. So, what we have here is that P is even. Now, we're saying that a sub 0 is positive, and we're saying the first term, the leading coefficient is 1, which is positive. So in terms of the sign changes, the first and the last have to be positive. Well, if they're all positive, then the sign change was 0. The first and the last have to be positive. The first one is 1, and the last coefficient is a 0, which in case number 1, we're assuming it's positive. So if you have a negative somewhere, just one negative, well then, you're going to have a sign change here and a sign change here. S is going to be 2. Well, what if I have, again, first and last positive. What if I have two negatives? So you have a sign change here, another one here, a third one here, and a fourth one here. So S would be 4. Well, what if I put the two sign changes right next to one another? Remember, the first and the last have to be positive. Well, we have one sign change, no sign change, and then a second sign change. Every time I add two more, or even one more, every time I add one more, we're going to have 1 and 2 like we had above. But then we have 1, 2 more. S is going to be 4. Okay, so what we have is that S will be even. So then S minus P, an even minus an even, will be even. So the number of sign changes minus the number of positive roots, if A is positive, must be even. Now, let us go on to case number 2. Let me just draw, okay, this is fine. So, A sub 0 is negative. And P of 0 is A0. That is, that point is on the graph. And remember that the limit goes to infinity. So at the end, the graph has to go up as we go to the right. Not necessarily initially, but at some point, goes up, up, and away. Should always label your axes. Okay, so we can have it like this. This would be where P is 1. Or it goes up and then comes down and just touches and goes up. Well, we have 1, 2, 3. Here, P is 3. Or it can go up. It has 1. And every time it comes down and goes back up. And when I say down, I mean crosses the x-axis or just touches it. We have the 1 because we went up. Up means above the x-axis. But then we have 2 more. P is 3. Every time it goes up, when it comes down, it's going to, and goes back up, it's gonna have 2 more roots. Even if you just touched it, it'll have 2 more roots. Then it comes down and it goes back up, it's gonna have 2 more roots. This polynomial is gonna have 1, 2, 3, 4, 5. P is 5. P is going to be odd. Now, A sub 0, the last coefficient is negative, and the first coefficient being 1 is positive. So you're going to have a positive and then a negative. If they're all positive in the middle, you're only going to have one sign change. If you have in the middle one more negative, well, then you're going to have one sign change, a second sign change, and then a third. If you put in the middle 2 together, you're going to have 1, 2, 3 sign changes. If you have 2 in the middle, but they're not together, negative, plus, plus, negative, plus, plus, plus. You're going to have one sign change, a second, a third, a fourth, and a fifth. S is 5. And one might argue, well, what if you put 2 at the end? then you're only going to have one sign change. And if you put 2 in the middle, or one more in the middle, you'd have 3 sign changes. We have that S is going to be odd. Well, if P is odd and S is odd, you subtract 2 odd numbers, you get even. So, whether A sub 0 is positive or A sub 0 is negative, we can conclude that S minus P is even. Okay, because if A is positive, we get even. If A is negative, we get even. We always get even. Okay, so now let's look at part 2. Part 2 is where I want to show that S minus P is at least 0, not negative. Okay. Part 2. Show or prove that S minus P is at least 0. Remember, to prove this theorem, we need to prove this. We need to prove this. And think about why this is sufficient. So, we want to prove that S minus P is non-negative, is a non-negative even number. That means we want to prove that S minus P is non-negative and it's even. Well, I just showed the even. Now I want to show that it's non-negative. And if I do show it's non-negative, then S minus P will be a non-negative even number, even integer. Yeah, even number. Okay. So we're on to part number 2. And part number 2 is going to be by induction. We're going to prove this by induction on the degree of the polynomial, on n. Now, if n is equal to 1, then f of x will just be, say, x plus a. Remember, we want the leading coefficient to be 1. Now, we're going to have 2 cases. If a is bigger than 0, then x plus a equals 0. That means x is negative a. Now, if a is positive, this root is negative. So, and that is the only root. That means the number of positive roots is 0. Now, what's the sign change? The 1 is positive, and I'm telling you a is positive, so there is no sign change. And it turns out that, yep, S minus P, which is 0, is greater than or equal to 0. Now, what if a is a negative number? So you have x plus a equals 0. Bring the a to the other side. Well, anytime, remember, a is negative. Anytime you put a negative in front of a negative number, you get a positive number. So the root, x equals negative a, is a positive root. And there's 1. Now what about the number of sign changes? Well, this coefficient is positive. And if a is a negative number, like x minus 5, well then, or 1 minus 5, then there is a sign change. And once again, s minus p is 1 minus 1, which is 0, and 0 is at least 0. So n equals 1 has been established. We got it. We have our base case. Now, for n equals k, we assume that for f of x equaling 1 x to the k, of course, the leading coefficient, we want it to be 1. If it isn't 1, you divide it through, and then this theorem follows. Plus ak minus 1, x to the k minus 1, plus a sub k minus 2, x to the k minus 2, all the way down to a sub 2x squared, plus a sub 1x, plus a sub 0. Assume for that polynomial that s minus p is at least 0. This is our assumption. Maybe we'll use it, maybe we won't use it. But when it comes to n equals k plus 1, I want to show that s minus p is at least 0. Okay. So now f of x will be 1 times x to the k plus 1 plus a sub k x to the k plus a sub k minus 1 x to the k minus 1 all the way down to a2 x2 plus a sub 1x plus a sub 0. Now, where do the sign changes come from? Sign changes, they come from this list of numbers in this order. 1, positive a sub k minus 1, all the way down to a sub 2, a sub 1, and a sub 0. Comes from that list. In other words, if this were 7 minus 3, 4, 9, 2, 8, negative 8, 3, well then, one sign change, a second one, a third one, a fourth one. You don't need to have the x to their powers. Okay. Now, so suppose that the number of sign changes, it has to be something. Let's call it S. I want to think if I want to call it S or not. Well, I'll decide in a moment. And then the number of positive roots, say that is P. Okay. Now, what we want to do is we want to compute the derivative. So let's just have this boxed. That way we can go back to it nicely. Now notice I never ever said that s minus p is greater than or equal to 0. That's what we want to show. Now it turns out that f prime of x is, taking the derivative of this polynomial here, will be k times 1 x to the k plus k times a to the k x to the k minus 1 plus k minus 1 a sub k minus 1 x to the k minus 2 all the way down to 2 times a sub 2 x plus 1 times a sub 1. 1 times a sub 1. And of course, the derivative of that constant is 0. Now, how many sign changes does this polynomial have? Now remember, this is a polynomial. That means that all of these powers, which I brought down in front, they're positive. I mean, you can argue this one is 0, but then again, I don't have it down here. That is no longer there when it comes to the derivative. Plus a 0. That is, this is positive. That should be k plus 1. Sorry. When I bring down the k plus 1 in front, it should be k plus 1. Okay, this is positive. This is positive. This is positive. This is positive. And the 1 is positive. So what's going to make the sign changes if we're going to have any? And the answer is it's going to come from these numbers. It's going to come from those numbers. Okay. The sign changes will come from this set of numbers. 1, a sub k minus 1, all the way down to a2 and a1. It's going to come from them. Why? In case you didn't get it. If this let's go here. If this number is positive, then multiplying it by a positive won't change the product. It'll be positive. If this term is negative, multiplying it by positive k still maintains the sign. That is, the sign of this product is determined by a sub k. This positive number times that unknown number. The sign of that product is going to come from a sub k minus 1. 2 is positive. When you times it by a sub 2, whether it's positive or negative, is going to come from the sign of a sub 2. Same thing with a sub 1 and same thing with 1. Okay. So that's why I say the sign number or sign changes in f prime is going to come from that list of numbers. Now, let us call this list, let us call that list star. And remember, star has X sign changes. And let us call this list double star. Double star. Okay? Now, the only difference between the two between star and double star is a Subzero. I mean, after all, this is double star, and what I just underlined is double star plus a Subzero. Okay. Now, there are two situations to consider. Suppose, well, and equals s prime, and the number of positive roots is p prime. Okay? The sign changes from f prime of x is S prime, and the number of positive roots is P prime. Now, suppose that A0 and A1 have the same sign. Okay? That is, those two have the same sign. Now, we said that just these, up to A1, the number of sign changes is S prime. That's this list, okay? Now, when you add on A0, which is the same sign as A1, then the number of sign changes for double star, then the number of sign changes for double star is gonna be the same. It's just gonna be S prime equals S. What we're calling it and what it is, I said equal. S prime equals S. Now, suppose A0 and A1 have different signs. Then the number of sign changes for double star is gonna be, well, let's be careful. All of these, let's go to this list. All of these have the number of sign changes is S. And it included this last one, because now they're different. But this list down here, it doesn't have A0. It's gonna have one less. S prime is gonna be S minus 1. Okay? S prime is gonna be S minus 1. So, since S equals S prime, well, let me say it the other way, please. Since S prime is equal to S, or S prime is equal to S minus 1, what can we conclude about S prime? We know that S prime is going to be less than or equal to S. It can equal less, or it can be one less than S. So, and if it's one less than S, then S prime can be less than S. So S prime can equal S, or it can be less than S. How much less? 1, but nonetheless less than S. Okay. Now, we need to find some information about P prime. P prime is the number of roots when it comes to F prime. Now, where are we? We said that f of x had p roots. Okay. Let the p roots of f, let the p roots of f of x be, let it be R1, R2, R sub 3, all the way down to the pth root. So let's just label them. And suppose we put them in order. R1, R2, R sub 3, R sub 4, all the way down to r sub p. Now, suppose, I'll just call them a and b. Suppose a and b are roots of f of x. It's one of these two roots, a different than b. So, f of a equals f of b. And f of x, being a polynomial, is continuous and differentiable on the correct domains. Okay. Now, by Rolle's theorem, where did this come from? By Rolle's theorem, we know that there exists a C in the interval AB such that f for C is 0. Another word, so we know there exists, I want to say it this time, there exists at least one C. Okay, so in between R1 and R2, there's a root for that derivative. At least one. In between R2 and R3, there's a second root. Notice, to the right of R1, we have a root. To a first root. To the right of R2, we're guaranteed a second root. To the right of R3, we're guaranteed a fourth root. Let me just write RP minus 1. And then r sub p. To the right of R4, we're going to have a fourth root. And in between here, to the right of r sub p minus 1, we're going to have a p minus first root. And there's no reason for there to be a root here. So we know. Now, there could be more. There could be more. There can be many in here. Many in here. Now let's go back and see what we call the number of roots in the derivative. Everything here was the derivative. So we said here that with respect to the derivative, it has p prime roots. Okay. So now, we know that, hence, p prime must be at least p minus 1. P prime must be at least minus 1. This is by Rolle's theorem. Okay. Now, by hypothesis, s prime minus p prime is at least 0. S prime minus p prime is at least 0. Now, this tells us that s prime is at least as big as p prime. Now, we know from earlier, I'll show it to you, that s is at least s prime. S. Now, let me just state why this is true by hypothesis. The reason is because the derivative is of degree k. And we know that any function, the derivative is the function. Don't get caught up, but wait a minute. It's the derivative. It's the function. And we're assuming that if a function is of degree k, that s minus p is positive. Okay. Now, I said that I was going to show you where we established that. Remember, we said that S prime was either S or it was S minus 1. That means that S prime is less than S. And if S prime is less than S, that means S is bigger than S prime. Now, we know that S prime is bigger by hypothesis. We know that S prime is bigger than or equal to P prime. But P prime is greater than or equal to P minus 1. We said that right here. Okay, so S is bigger than or equal to P minus 1. That is, S minus P is at least 1. Is at least negative 1. But an hour ago, we showed that S minus P is even. So, if you, now here's a number line, here's negative 1. If you're an even number, bigger, either negative 1 or bigger. If you're an even number, well then, either, you're at least 0. You're an even number bigger than 0. 0 or 2 or 4 or 6. So, you don't need that in the proof. So, S minus P is at least 0. And that completes the proof of Descartes' theorem. Now you may say, well, you didn't do the proof for negative numbers. For negative roots. In my opinion, that shouldn't be and probably isn't in the full statement of the theorem. This is the theorem. A consequence of this theorem is the negative. Remember, if you have some polynomial, and then you look at P of X, maybe here, we'll do it. 3x squared, not minus. Let's erase it. Suppose you have 3x to the 5th minus 2x to the 4th minus 3x cubed plus 4x squared minus 5x plus 9. Well, P of x will be P of negative x will be negative 3x to the 5th minus 2x to the 4th plus 3x cubed or plus 4x squared plus 5x plus 9. But this is just another function. Now, suppose, and we're going to call this function f of x, but we know in disguise it's p of negative x. Suppose that p of negative 3 equals 0. That is, it probably isn't, but let's suppose when I plug in negative 3 here, I get 0. Okay? But this is going to imply that f of 3 equals 0. Why? Because f of 3, so I plugged in 3 for x, I better plug in 3 for x here. It's not my fault somebody put a p and a left bracket and then a minus sign and then a 3 and then another bracket. And yes, p of negative 3 is 0. That is, I can use the negative p of negative x to find, in disguise, I can find the positive roots of this, but in reality, it's the negative roots of p of x. Okay, I'm finding the positive roots of this. And 3 is going to be a root. f of 3 is going to be a root because f of anything is equal to p of the negative anything. So that's just what I would call a consequence or a corollary. Now, why was this sufficient, this being this right here? Why was this sufficient to show? Well, I showed that s minus p is at least 0. Okay? And I also showed that it's even. So for the difference. So if s is 7, that means that p can be 7 or 5 or 3 or 1, which is exactly what we want to show. If s is 7, if there are 7 sign changes, then p can be 7 or decreased by 2. Because it has, s minus p has to be even. 7 minus 7 is even. 7 minus 5 is even. 7 minus 3 is even. 7 minus 1 is even. That completes the proof. I even justified why, showing that this was sufficient. Okay, why did it have to be positive s minus p? Think about that. Think about why the number of sign changes has to be bigger than the number of roots. Positive roots. It's in here. Look for it. If you just love videos like this, please subscribe to my channel. Most of all, watch and learn. See you in the next video.